So right now we're going to take a look at a particular kind of matrix. All right, so we're going to introduce this idea of a non-singular matrix. Okay, so up to now we've looked at different techniques for solving systems of equations, so right, homogeneous or otherwise, right, non-homogeneous uh, systems of equations. So here, right, we're going to take a look at this idea of a non-singular matrix, right? So as we kind of work through this section and just in general in this class moving forward, it's very important that we use the proper language, right? So just keep in mind, right? A matrix is not a system of equations, right? And vice versa, right? A system of equations is not a matrix. We use these objects here to help us solve or represent systems, but they are two separate objects, right? So what we're going to take a look at here is um, we're going to first this idea of a non-singular matrix. Now it's a property that is subscribed to a certain type of matrix, right? A matrix, first of all, has to be square, right? So when I say a square matrix, what I mean that the rows and the columns are equal, right? So equal number of rows and columns, right? So example here, a 2 by 2, right? Right, so that is a general 2 by 2 square matrix, right? 3 by 3. Right, so these are examples. We have a 2 by 2 square matrix and a 3 by 3 square matrix. All right, so when we say a square matrix, we're referring to one that has an equal number of rows and columns. And if it is not square, then it is a rectangular matrix, right? When the columns and the rows are not equal. And we call that a rectangular matrix. All right, so when we talk about this idea of non-singular, it is referring to this property applies to square matrices, right? Now, not all square matrices are non-singular, right? But some of them are, right? And this is so. Now let's define what is a non-singular matrix. Non-singular matrix. Okay. So a non-singular matrix is a square matrix. All right. So here, so a non-singular matrix is, let's say we have it applies to a matrix A. We suppose matrix A is square. Okay. So it's a square matrix, and suppose also that the solution to the linear system, so solution to the linear homogeneous system, right? So if we think of A as the coefficient matrix, right, then the linear system uh, is the zero vector only, right? So in other words, it has only the trivial solution. Okay, so if those two conditions are met, right? First of all, it's square, and that the solution to the homogeneous linear system of this matrix A is the trivial solution. If those two are met, then we say that then A is non-singular. Okay. And if we say A is singular otherwise, right? So if A is singular, then it has more than the trivial solution, right? And as we've discussed before, right, if it is a homogeneous system, then it will at least have one solution, right? So we know that that system will always be consistent. It's just a matter of determining whether it has only the trivial solution or infinite number of solutions. Okay, and if it has the infinite number of solutions, right, then it is non-singular. And if, excuse me, singular. And if it has only the trivial solution, we call that a non-singular matrix. All right, so here, if we start to think, all right, what do these non-singular matrices have in common here, right? So if we think of, okay, any kind of system of equation that we have, all right, so if we think of a general, right, 3 by 3 matrix, all right, now if we think of, okay, what would cause this if I were to do the reduced row echelon form, right? So again, we'll think of this as the coefficient matrix, right? What would that look like, right? What would the matrix here, what would its reduced row echelon form look like? All right, so if we think of going through the row operations, and I know that it is singular, excuse me, it would be non-singular, right? Well, then that means that it would only have the trivial solution. Well, that means that it would have to reduce row echelon form to this particular form, right? Because then it would have to have these 3 pivots here, right? That would make it a non-singular matrix. Okay, now as it turns out, this type of matrix here that has in reduced row echelon form has a particular name to it, right? So that is what we call an identity matrix. All right, so this is called an identity matrix. All right, so an identity matrix is always a square matrix. This one we'll call I3, right? Where we have ones along the diagonals, right? So when we say diagonal, we're referring to this part of the matrix, right? The one that starts where the row and when we're referring to it, the row and the column subscript are the same, right? A11, A22, A33, right? So in general, we define a matrix, an identity matrix, IN, to be equal to, all right, in general, it's here. Okay, so here, an identity matrix, I sub n, ij, right? So it is, the elements are 0 when I does not equal j, and 1 when I is equal to j, right? So all this here has the behavior that shows with this I3, right? When the I and the j, in other words, when we're along the main diagonal there, right? When those values are 1, everything else is 0, right? And it turns out here that, well, if it's going, again, only dealing with square matrices, if it's going to have the trivial solution, I will always have to wind up in this situation, right? Because if I didn't, let's say I did have a 3 by 3 and it wasn't in this identity, well, if it's in reduced row echelon form, then it would look something like this, where this is just some constant, right? Let's just call it some constant k, right? It would look like that, and in that case, that would be infinite number of solutions, right? and we would have this would be an example of a singular matrix. Right. So as it turns out, this idea of non-singularity, right, is related to this. Well, if we apply the reduced row echelon form, then we will always get the identity matrix, right? And here, let me switch over to our textbook here, and let's introduce here a theorem. Okay, so we're taking a look here at theorem NMRRI. And this states that, so the theorem is non-singular matrices row reduced to the identity matrix. And again, we start with our assumptions. A is a square matrix, and B is a row equivalent matrix in reduced row echelon form. Right, again, row equivalent in that we just perform row operations, valid row operations to A to get the matrix B. All right, and so our theorem states then A is non-singular if and only if B is the identity matrix. All right, so here, let's kind of parse through that theorem here. Okay, so here, so we have our assumptions here. Our assumptions is that A is a square matrix. And B is row equivalent to A and in reduced row echelon form. Okay, so if those are our assumptions, then what we can conclude, what the theorem states, is that then A is singular if and only if B is the identity matrix. All right. Okay, and this provides a very strong relationship between these two ideas, right? When we see that if and only if statement, that's much stronger than an implication if then statement, right? So A is singular if and only if B is the identity matrix, where B is row equivalent to A and in reduced row echelon form. Okay, so here, right, and just keep in mind when I say this if and only if, right, it it means that our implication statement, right, if A is singular with the above assumptions, if A is singular, excuse me, if A is non-singular, then B is the identity matrix. Right? And also if B is the identity matrix, then A is non-singular. All right, so this is the idea of it going in both directions, right? Now, this doesn't always work for these if-then statements. When you do switch them around, right, write the converse, that's not always guaranteed to be true, right? But for this type of relationship, if and only if, right, it's what's called a biconditional, right? Then both of these statements are true, right? It's a much stronger relationship, right? One implies the other, and the other implies what we started with. Okay, so now we have a way to identify excuse me, A is non-singular. Sorry about that here. Okay, glad I cut that now. A is non-singular. Okay, so A is non-singular if and only if B is the identity matrix. All right, that is the theorem. All right, A is a square matrix, B is a row equivalent matrix to A. All right, so it's almost like a definition, right? Much stronger than just a theorem, an implication, right? We're defining what it means to be a non-singular matrix.